Alright, this is the first of 2 videos on experimental design. Hopefully you learn a lot about what it takes to create a good experiment while you watch this video. So first, the point of any experiment is to determine the impact of an explanatory variable has on a response variable. So we talked about the explanatory variable and the response variable. To see this clearly, a lot must occur. Remember, the idea here is that if we do an experiment well, we could actually say that the explanatory variable causes a change in the response variable. But to do that, it's got to be a good experiment. So first thing I want to talk about here is who is involved in an experiment. There are 3 major groups of people involved in an experiment. First is the researchers. The researchers are you, right? I mean, you are the one creating the experiment. You are the one that knows everything. You're the one that organizes everything. Somebody has to be like the Wizard of Oz, right? The person behind it all. Okay, that's the head researcher. Then you have your subjects. Now, the subjects are the people that are actually going to be involved in your experiment. Now, they're not always people, so oftentimes we refer to them as experimental units. Subjects are really only if they're people, but they could be, it could be land, it could be dirt, it could be trees, it could be animals. It could literally be anything that you could experiment on. So in that case, we'd call them experimental units. And also, we need somebody to be the evaluator, somebody to measure the response. So the evaluators is the person that measures the response. Now you might say, well, why doesn't the researcher do that? Well, the researcher could do that, but typically sometimes your response variable might be something that the researcher is not educated on, and the researcher needs to hire a professional that can actually do that evaluating for you. And we'll talk about that as we go through the examples here. Now, in an experiment, researchers actually give out something to the subjects, right? That's the difference between an experiment versus an observational study, is the researcher actually gives something out. And what we call what they give out is a treatment. We call the actual what they give out the treatment. So I have 3 examples I want to look at here, and I want to talk about the treatments. So first one says, researchers want to know, does vitamin D help reduce the length of a cold? So what are we going to give out? Well, we're going to give out a group that gets vitamin D. And we also need a group to compare it to so we could see if it actually is better than nothing. But maybe vitamin D is best in small doses, or maybe it's better in large doses. So, we might end up giving out 10 milligrams of vitamin D. Another group might get 20 milligrams of vitamin D, and another group might get 30 milligrams of vitamin D. And lastly, we might have a group that gets 0 milligrams of vitamin D, just to make sure that the vitamin D is actually doing anything at all. So again, we have vitamin D as our explanatory variable, but that means we have several treatments. A treatment is the actual things that you give out. So we're going to give out 10 milligrams, 20 milligrams, 30 milligrams, and 0 milligrams of vitamin D. So those would be our treatments. Again, what we're giving out. Researchers want to know how much water and fertilizer produces the tallest, thickest grass. Well, maybe we think that water helps grass grow, obviously, and we could water 1 time a day, we could water 2 times a day, or we could water 3 times a day. But also we have fertilizer A and fertilizer B, and we're not quite sure which one is better. So we have 2 explanatory variables, water and fertilizer. Both we want to produce taller, thicker grass. That's our response variable. But because we have 2 different explanatory variables, and one comes in 3 values, or 3 levels, one comes in 2 levels, we actually produce 6 treatments. Okay, so let me list them all for you very carefully here. So the first would be treatment A, or fertilizer A, 1 time a day, A 2 times a day, and A 3 times a day. Then we got B 1 time a day, we got B 2 times a day, and we got B 3 times a day. So we actually have 6 treatments given out. Fertilizer A, watered once a day. Fertilizer 2, watered twice a day. Fertilizer A 3 times a day with water. B 1 time with water. B 2 times with water. B 3 times with water. I guess you could have some grass that gets no fertilizer and no water, but common sense would tell us that we know that grass isn't going to grow very well at all, so that's not necessarily needed. Okay, what is the best time and temperature to cook perfect chocolate chip cookies, right? We want the best tasting chocolate chip cookies, so we have 2 things. We have explanatory variable time and temperature. So we have 2 explanatory variables, and it's our job as a researcher to come up with a treatment. So maybe we do 20 minutes at 300 degrees. Maybe we do 20 minutes at 350 degrees. And maybe we do 20 minutes at 400 degrees. Sorry, this should be 20 minutes at 400 degrees. But maybe we think that, oh, well, maybe 25 minutes is better. So we're going to do 25 minutes at 300 degrees. And 25 minutes at 350 degrees temperature, and 25 minutes at 400 degrees. Again, your job as researchers to think, what different times are you looking at? What different temperatures are you looking at? Then you got to put all of them together for it to really be fair. So this would, again, have 6 treatments. Again, maybe you want to also explore 15 minutes. Well, then you got to have 15 minutes at every temperature. If you don't have one of those combinations, then you're not quite sure that what you're doing is best. So you got to make sure you think about the different treatments that you can give out, even if you only have 1 or 2 explanatory variables. Okay, now when we work with people, we have a very interesting problem. Now, if people know they aren't getting any treatment in an experiment, this fact alone could change the response variable. This knowledge could therefore be a confounding variable. Let me give you an example. If I bring in a group of people and half of them are going to get vitamin D and the other half are not going to get vitamin D, and I openly tell the group of people that is not getting vitamin D, sorry, you're getting nothing. That fact alone might make them upset, it might make them feel depressed, and then all of a sudden the length of their cold is extended because of that simple fact. It also could work the other way. When people know they're getting a treatment, it might affect the response. So if people are told, congratulations, you're a part of an experiment, you're going to get vitamin D, we think it might help the common cold. Well, then all of a sudden the excitement, the energy that's involved in them knowing they're getting something might actually affect the response. This idea is called the placebo effect. The placebo effect is the idea that when you're working with people, when they know they're getting something or they know they're not getting something, the outcome could change simply because of the excitement of being in an experiment itself. So it's actually really hard to control for this, but what we can do is we can give everybody a treatment. Everybody gets something. And what we do is to give somebody something even though they get nothing, that's where we use a placebo. So placebo is a fake treatment that's acting like something so that people think they're a part of something, right? So here's the idea that I need you to understand. You cannot get rid of the placebo effect. You cannot have some people being excited and some people being depressed. You cannot get rid of the placebo effect. But what you can do is you can allow everybody to experience the placebo effect by giving everybody a treatment, which means you may have to use a placebo when you're working with people, because people know when they're getting something versus when they're not. So to compensate for that, everybody gets something, and again, this is to control for the placebo effect, not get rid of it. So that's a problem. You don't really have this problem when you're working with animals or inanimate objects. Okay, now, when we're talking about an experiment, there are 4 major pillars for a good experiment. 4 major big concepts that every experiment must incorporate. And we're going to go through the 4 of them now. The first is comparison. Every experiment must have at least 2 treatment groups to compare. One can be a control group, and a control group is often the group that gets nothing. A control group is used for comparison alone. And when you're working with people, we oftentimes have to give them a placebo, again, a fake pill. Now, why do we need 2 treatment groups or more? Well, think about it. If I want to know that if vitamin D helps shorten the length of the common cold, and everybody gets vitamin D, then all I'm going to know is how long everybody taking vitamin D took to get over the cold. I'm going to have nothing to compare to say, oh wow, it's really better than not taking vitamin D. So I need at least 2 groups, at least one group that gets vitamin D and one group that doesn't get vitamin D. Same thing with my fertilizer example. If everybody got fertilizer A watered twice a day, all I'm going to learn is that fertilizer A twice a day either makes grass grow or doesn't make grass grow. I'm not going to learn if it's better than another method, another treatment of doing it. Same thing with my cookies. If I cook all the cookies for 25 minutes at 350 degrees, okay, I'm going to learn how those cookies taste, but I'm not going to learn if it's truly better than another temperature or another time. So that is the point of you having to have at least 2 treatment groups to make it work. You can have 2 or more, but you can't have only one. If everybody gets the same thing, then you're not really going to learn anything from that experiment. So you've got to have that comparison idea. All right, the second major pillar is randomization. Randomization is in which subjects get which treatment must be handled by random assignment. Subjects cannot choose because their choice could be a confounding variable. So, for example, if I want to know what exercise program is better, exercise program A or exercise program B, which one's better at making you more physically fit? Well, if I allow people to choose what program they go into, well, that choice alone could become a confounding variable, because maybe Mikey chooses to go with his best friend Jimmy, and all of a sudden Mikey and Jimmy are competing, they're pushing each other, and they both got more physically fit because they chose to go together, they pushed each other, they worked hard. They would have done that if they were in the other group as well. So you cannot allow people to choose what group they go into, because that can become a confounding variable. So it's got to be done randomly. So let's review the 3 steps to choosing random groups. First, all the subjects would get a unique number. Second, use a random number generator, which could be a random number table or your calculator. Make sure you ignore repeats, because Jimmy can't be picked to go into both groups. And make sure that you ignore numbers outside of your range. And then the first N people chosen would get treatment 1, the next N would get treatment 2, the next N would get treatment 3, and so forth. If you only have 2 treatments, the first N get treatment 1, everybody else gets treatment 2. But how you pick those people must be random. A big part on a lot of AP tests is being able to explain how are you going to randomly assign your subjects. I'm outlining it right here for you. Every subject gets a unique number. Let's say you have 30 people. Every subject gets a unique number, 0, 1 through 30. I will use a random number generator. I ignore numbers above 30. I'll ignore 0, 0. I'll skip repeats. The first 10 people get treatment 1. The second 10 people get treatment 2. And the last people remaining will get treatment 3. Whatever it takes, it's got to be done randomly. All right, now, replication is another major pillar. Replication is the idea of using many subjects in each treatment group to reduce the impact of variation arising from random assignment. Now, that may sound a little bit confusing, but I promise I will clear that up in a moment. Now, I'll kind of make that a little bit easier to understand. Basically, you need a lot of subjects, right? Anything's better than one. A lot of kids say, well, how many subjects do I need? Or how many should we have in each treatment group? Well, if you have 2 in each treatment group, 2 people in each group, hey, that's better than 1. 5 would be better, 10 would be better, 20 would be better, heck, 1,000 would be better. Anything's better than 1. So there's no set number, but you need a lot. Now, why? Why? Well, we want to use enough subjects in each group so that any differences in the effects of the treatments can be distinguished from chance differences between the groups. Now, this confuses a lot of people, so I make sure you write these 2 things in blue down here dealing with replication, and I really want to make sure I explain why. Using many subjects in each treatment group to reduce the impact of variation arising from random assignment. Now, pause it if you need to write down those statements, and then hit play again, and I'm going to try to use an example to explain this. All right, let's go to our example of vitamin D in the common cold. Let's just say that I have 10 subjects that are willing to do this experiment. Half of them are going to get vitamin D, and the other half are going to get a placebo. Why am I using a placebo? Because if I tell people they're getting nothing, then that might affect their response. Again, I'm trying to control for the placebo effect by giving everybody something. Well, I'm going to use random assignment. Well, that's one of our pillars, right? And I'm going to give randomly 5 people will take vitamin D, the other 5 will take a placebo. Now, here is the problem. What if these 10 people had 5 were old people and 5 were young people? Now, I'm supposed to do it randomly, but because I only have 10 people, it would not be that weird or that unlikely if all 5 of these people were old and all 5 of these people were young. Well, guess what? I just introduced a confounding variable. Now, all of a sudden, if this group up here that takes vitamin D gets better, maybe they took longer to get over the cold, maybe they took shorter to get over the cold because of their age, not because of the vitamin D. And that's a problem. Now, we hope random assignment would not put all 5 old people together and all 5 young people together. But when you only have 10 people, that is possible. Now, imagine if this was 100 people now, right? 50 are going to take vitamin D, 50 are going to take a placebo. Now imagine if I have 50 old people and 50 young people. It would be extremely unlikely. I'm talking very, very unlikely for all 50 old people to get put into the vitamin D group and all 50 to go to the young group. That's because I'm using a lot of people. With only 10 people, I could get 5 old people all together by just randomness. But if you have 100, the chances of you getting 50 old people all to go into the same group would be literally, I mean, I can't say literally impossible, but it would be really, really close to impossible. So then all of a sudden I wouldn't have this issue. And that's what I was trying to explain down here. So if I go back down here, now this should make sense. Using many subjects in each treatment group to reduce the impact of variation arising from random assignment. So if I use random assignment, it could happen where I get the 5 old people and the 5 young people. But if I use more people, the chance of that happening diminishes, right? I want the only difference at the end to be who was taking vitamin D and who wasn't. And if I use more people, any subtle differences that happen, like age, like gender, like genetics, like health history, any of those weird things that you can't really control for, well, the more people you use, those other variables become diminished. Okay? The idea is that I want these two groups of 50 to be as similar as possible. And if I use more people, I make the groups more similar. Even if you talk about, well, these 100 people are all very different. I get that. But if I only use 10 or if I only use 5 people in each group, well, 5 people could really be impacted by something like age or something like gender or something like medical history. But 50 people, it would be harder for one other variable to impact the group. So that's why we really have to have that replication idea so that way we have as many people as possible. And heck, if I'm making it up, I would rather have 1,000 with 500 and 500, right? The more the better. The more people you use, the less those other variables are going to play a part in your experiment, okay? And I'll read this bottom statement one more time as well. We want to use enough subjects in each group so that any differences in the effects of the treatments can be distinguished from chance differences between the groups. What we're trying to say is that we want to see at the end, we want to see the differences in the treatments. Vitamin D versus no vitamin D. And when we have more people, it's easier for me to see those differences if I have more people. Okay? And it can, in all those other variables that could happen because of random assignment become, well, less important when I have more people. So hopefully that idea makes a lot of sense to you, and that's typically a pretty important AP question to understand why we need replication. Okay? All right, the fourth and final pillar of any good experiment is control. The idea with control is we want our treatment groups to be as similar as possible to reduce variation. We want our groups to be as similar as possible to reduce variation. Remember, variation is the fact that people vary. Well, I don't want my two groups to vary. I want my two groups to be exactly the same. The only difference is what treatment we give out. Okay? Anything that can affect the response must be the same. To kind of put everything together, all the 4 pillars, I want to take a look at our examples that I brought up earlier and try to point out some of these things. So, can vitamin D shorten the length of the common cold? All right, let's just say that I have 1,000 subjects. Let me talk about these subjects. Well, I need them all to have the common cold, right? And I need them all to have started the common cold within the last week, because if somebody's already at the end of the common cold versus at the beginning of the common cold, then that could become an issue with how long the cold lasts. Makes sense, right? But remember, it's going to be hard to make sure everybody just started the common cold. So the idea is if I have more people here, those small differences will be diminished. That's the idea of replication. Using enough people, that way those other variables, like when they got the common cold, their gender, their age, their medical history, all of those things are diminished, right? Now, I'm going to take 500 of them, and I'm going to give them vitamin D, VD, vitamin D, and I'm going to give the other 500 of them a placebo. Again, hopefully by now you understand why I'm giving them a placebo. Could I have another group that gets a little bit more vitamin D or a little bit less vitamin D? Absolutely. But remember, you got to have at least 2 groups for comparison, right? Now, what are some things that I want to keep the same for these people? Well, I want to tell everybody, first off, what are some things that could affect the response, right? The response is the length of the common cold. People say that how much you exercise could contribute to how long the common cold is. Well, I can't really make people exercise more, make people exercise less, but if I have 500 people in each, the random assignment, I'm going to put a capital R here for random assignment, the random assignment should put people that exercise into both groups, provided I have a lot of people, which I do with 1,000. What about age? Age is something, older people take longer to get over colds. Well, once again, with using 1,000 people and random assignment, hopefully I'm going to put older and younger people into both groups, making my groups similar. Some people might say that drinking orange juice. Okay, well, one thing I could do is tell everybody, tell all 1,000 people, sorry, no orange juice for the entire length of this experiment. That could work, or if you feel that that's hard to do, you're just going to have to make sure that the people you use, well, random assignment should put people that drink orange juice in both groups and people that don't drink orange juice in both groups. So again, that's the idea how random assignment and replication really can kind of help get rid of some of those other variables that affect the length of the common cold. All right, let's talk about how much water and fertilizer produces the best grass. So how am I going to do this? Well, let's just say I have 100 plots of land. Okay, 100 plots of land. And I'm going to give out, some plots are going to get fertilizer A, watered 1 time a day. Some are going to get fertilizer A, watered twice a day. Some are going to get fertilizer A 3 times a day. Some are going to get fertilizer B 1 time a day. And sorry, this is kind of getting a little bit longer here, but vitamin B, fertilizer B twice a day, and fertilizer B 3 times a day. Now, what are some things that I should keep the same? What are some things that I should control here? Well, I want all the same dirt, because I don't want the dirt to affect the grass. All the same sunlight, right? All the same shade. What about wind? Well, it's all the same amount of wind. Well, what about animals that could come around and eat my grass and make it not grow well? Well, put a fence around your land. You have to establish control. That way these 100 plots are treated all equally except for what treatment they're getting. Now, is 100 divisible by 6? Well, when you take 100 and divide it by 6, I don't believe it's divisible, right? So you have to give maybe 16 go here, 16 go here, 16 here, 16 here. So that's 16 times 4. And then I got 16 here, and then 20 go here. Okay, you know what? Not the end of the world. No one ever said that every group has to have the exact same amount, but you should have enough, again, for replication. So again, the idea of control is keeping all these other things the same except for what fertilizer and what water you give out. Those are some important things to think about. I have plenty of groups to compare, and all that stuff is really, really valuable, okay? All right, now, how long and what temperature is the best for produces the best tasting cookies? All right, so let's just say that I have, I can't just have 1 cookie, right? I need to have a lot of cookies. So I'm going to do 200 cookies, right? 200 unbaked cookies, okay? Because I have to start unbaked, right? What are some things that I need to keep the same for these 200 cookies? Well, same oven, because I don't want the oven you use to become a confounding variable that impacts the taste. Same cook, right? Who's going, or the same baker, I guess. I think you're called a baker when you're doing cookies. So I don't want Sally to be a better baker than Kelly, so I'm going to make them use the same baker, made all 20, with the same recipe, right? With the same ingredients. If the only thing I want to look at is temperature and time, well, then everything else must be kept the same. Then I'm going to have my 25 minutes at 250 degrees, 25 minutes, I think I did 300, 350, and then 25 minutes at 400 degrees. And then maybe you could do the 20 minutes, 20 minutes, 20 minutes. You get the idea. Don't want to bore you here. But the idea is that I only want the only differences between those cookies to be the time and the temperature. So all those other things need to be controlled for. I got replication because I got 200 total cookies. That's going to put a lot of cookies into each group. I have replication. I have comparison. I have randomization. How do I have randomization? Well, okay, every cookie gets a number, and I'm going to use a random number generator, and the first 20 cookies are going to go here, the next 20 here, the next 20 here, and so forth. You want your groups to be as similar as possible. Okay? Now there's one more simple topic to go over real quick with you, and this is the idea of blinding. Okay? When you're working with people, you want to blind them to what they're getting. Okay, you don't want to tell people, oh, you're getting a placebo, you're getting the vitamin D. That defeats the whole purpose of using a placebo. So we have single blind means that the subjects do not know what they're getting. So the subjects have no idea what they're getting. Okay, and double blind is when the subjects don't know what they're getting and the evaluators don't know what they're getting. Once again, right, if we want to get a true person to taste these cookies, we don't want them to know what time and temperature they got. We just want to say, here's a bunch of cookies. We're the researcher. We know. We want you to tell us what ones are the best, right? Somebody has to evaluate my subjects to make sure that the common cold is gone. I need a doctor to come in and make sure that their cold symptoms are gone. I don't want that doctor to know. The doctor should be blinded as to if they got vitamin D or not, because I don't want that doctor to be biased in any way. Whoever's going to come and judge my grass and tell me if it's thicker, taller, greener, again, I don't want them to know which grass got what fertilizer or how much water. That way I get a complete unbiased opinion. So single blind, the subjects don't know. Double blind, the subjects and the evaluators don't know. So that's it for the basics of an experimental design. Hopefully you learned a whole lot and will be ready to work in class on this.